All right. What we're going to see today is finally arriving at a practical algorithm for computing all the eigenvalues of a general square matrix of a QR algorithm. So at this point, all we have is um, repeatedly computing the QR factorization and then multiplying the factors in reverse order after first reducing a matrix to one that has the same eigenvalues but is upper Hasselberg, just so each QR factorization and matrix product will be faster than in the general case. But that's still so meaningful progress was made last time, but there's still more to do. Okay. So, all right. So this is again progress that has been made to this point. Each iteration takes n squared work instead of n cubed like it did originally. But we're not done because even with that, okay, so each iteration is okay, but there are too many iterations. Convergence to an eigenvalue revealing form, if it is upper triangular or at least block upper triangular, still takes too long. So we want to try to achieve convergence to that form more rapidly. So what we're going to do is we're going to modify this approach of taking QR factorization of your matrix and then multiplying the factors in reverse order by shifting the matrix and carrying out those operations. So to motivate this, sorry, I need to find the right lines to comment out here so I'm not so I don't get LaTeX errors. Dang it. Okay. All right. So how fast is convergence now? To get an idea of why it can be bad. So for rate of convergence of subdiagonal entries of our Hasselberg matrix H to 0. So to recap, H being a Hasselberg matrix is upper triangular, but with one extra subdiagonal. So it's not entirely upper triangular. We have these at most one entry in each column that is below the diagonal that right below the diagonal that we want to try to make 0. So to get this upper triangular form, we need to keep applying transformations to H to make these subdiagonal entries 0. How rapidly do they go to 0? This is how fast. So so if we use a convention that we have been using, that lambda 1 is the largest eigenvalue followed by lambda 2, etc. Each subdiagonal entry goes to 0 at this rate, and that can be very slow if these two eigenvalues are very close together in magnitude. If they're equal in magnitude, but still different, like if they're opposite signs or they're complex conjugates, then they don't go to 0 at all. And so convergence might not occur. So, okay. So what can we do about that to change this convergence rate, to make this, we want to make this ratio smaller if we can. So what we do is, suppose we shift h by a scalar mu. So instead of working with h, we work with h minus mu times the identity. So mu is being subtracted only from the diagonal entries of h. So what we do is we form this matrix, QR factorize it, and then we multiply the factors in reverse order like we have been doing, and then we add the shift back. So here's what the algorithm is now. This taken into account. Shifted QR iteration. So here's our original square matrix A, it could be any square matrix. We reduce it to Hasselberg form using the algorithm that I described last time. And then we carry out iteration on this Hasselberg matrix. So we choose some shift. Now, we don't know yet how to choose a shift. That's something I'll talk about momentarily. But once we've chosen one, we go ahead and QR factorize the shifted matrix, and then multiply factors in reverse order, add the shift back. Now, to first explain why this is even valid, we're going to show how each new Hasselberg matrix relates to the previous one. So this is how hk plus 1 is obtained. This is a line straight from the algorithm. But then if we see how that's obtained, rk comes from qk transpose times the matrix to qr factorizing. So in general, if A equals QR, R is Q transpose A. So that's what I filled in here in place of RK. But then, if I distribute the QK transpose through here and also the QK, then I have this. But QK is an orthogonal matrix, so this is identity. So these terms cancel. And this is what you're left with. So each new Hasselberg matrix is a similarity transformation of a previous one. So this proves that the eigenvalues are preserved from one iteration to the next. And this is exactly what we had before in the QR iteration before we started shifting. So all I'm just proving is that when we do shift, as long as we add the shift back, it's still a similarity transformation of a previous one. Now, the thing is, because we're QR factorizing this shifted matrix instead of the original, the QK will be different. So it will be a different similarity transformation in this QR iteration than when we don't shift, with the idea that hopefully it's a more effective similarity transformation. So what does this do to the convergence rate? So before it was lambda p plus 1 over lambda p. So now numerator and denominator are shifted because basically we're performing this iteration on the shifted matrix. Anytime you shift, like you subtract mu k times identity, that subtracts mu k from all the eigenvalues. So what can we do to make this ratio smaller than the previous one? Well, certainly if mu is close to this eigenvalue, then we can drive this convergence rate to something near 0. So then we get very rapid convergence. So at least because recall when I described a convergence rate before, this is how fast a subdiagonal entry will converge to 0. So if mu is close to one of these eigenvalues, that means that one of these entries will go to 0 very rapidly. Okay. Now, in fact, what can be shown is if HK is an unreduced Hasselberg matrix. Now, this term is very important. I introduced it last time. A Hasselberg matrix is unreduced if all of the subdiagonal entries are non-zero. So if it's unreduced and mu k actually is an eigenvalue of HK, then what will happen is the last subdiagonal entry will turn out to be exactly zero. So you get immediate decoupling. In other words, one step of this form will immediately reveal mu k to be an eigenvalue. So if you're lucky enough to choose an eigenvalue to shift by, then it'll compute that eigenvalue right away, and then the problem will decouple, so then you can focus on the rest of hk plus 1, like excluding that last row and column, to find the rest of the eigenvalues. And that's what we want. We want to keep having this decoupling effect to work with smaller and smaller matrices until all the eigenvalues are found. Now, of course, we can't count on being lucky enough to shift by an eigenvalue, but that's okay, because even if mu k can be close to an eigenvalue of hk, then what that means is this matrix is nearly singular, because if mu k is nearly an eigenvalue of hk, then 0 is nearly an eigenvalue of this matrix. So the columns turn out to be nearly linearly dependent. Now, why is that important? That means that the last diagonal entry of RK from a QR factorization will be small. And then that would imply that when you carry out this transformation, the last subdiagonal entry will also be small. And therefore, the last diagonal entry will be nearly equal to your shift. So trying to get close to an eigenvalue, if there's any way to even get a crude estimate eigenvalue that can help drive this last subdiagonal entry to 0. So what that means is the problem is almost decoupled. And so then this is closer to an eigenvalue. So then we can use this diagonal entry as a shift for the next time and drive it even closer to an eigenvalue. So this is what's driving what's called the single shift strategy. That you take the last diagonal entry, the NN entry of your matrix, your Hasselberg matrix, use that as the shift. Because if the last subdiagonal entry is much smaller than this, then using that shift will make it smaller still, and so it'll just keep whittling away at it until it's 0. Now, how fast can it go to 0? It can actually be shown to converge to 0 quadratically. Now that's very important. When something is converging quadratically, that means that with each iteration, the number of correct decimal digits roughly doubles from one iteration to the next. So generally, you can only expect like 15, 16 digits of precision anyway. So if your accuracy is doubling from one iteration to the next to get to 15 or 16 digits correct, that's only 4 iterations. So that means you can pick off one eigenvalue in just a very few iterations and move on to the next one. So it'll turn out to be a lot fewer iterations than if you weren't doing any shifting. So quadratic convergence is something we really like to have. Now, now the thing is, before with a like power method, convergence is generally linear. But the reason why we can improve to quadratic is because we are changing the shift from one step to the next. So that shift is always improving, therefore making convergence even faster. Okay. So now I'm going to show you an example. Get an idea as to why we get this quadratic convergence. Okay, so just a 2x2 example. And when we're using the n entry as a shift, after we do the shifting, then this entry will be 0. So let's suppose this subdiagonal entry is epsilon, and we want to try to make it smaller. So what we do is we compute the QR factorization of this matrix, because it's already been shifted. And since it's a 2x2 matrix, you can get the QR factorization by only zeroing this entry. That just takes one Givens rotation. So I do that Givens rotation. And then what happens when we get the new matrix HK plus 1? What does that look like? Okay. So now I do a similarity transformation where this is RK from a QR factorization. And then I multiply the factors in reverse order. And so I just go ahead and carry out the matrix multiplication here. And this is what I get. But now if I go back to my formulas for the cosine sine pair in my Givens rotation, notice that the sine part is order epsilon. So, and notice that here, that sine is squared. So if I fill in what my cosine and sine are, well, I really only care about this subdiagonal entry. This is what I get. So sure enough, it's order epsilon squared. So if this entry is small to begin with, then after I perform one shifted QR iteration step, it's much smaller still. That's what happens when you take numbers that are small. You square them, you get much smaller. So this indicates why we have quadratic convergence of a subdiagonal entry to 0 when we carry out this shifted QR iteration using this single shift strategy. So to give a more concrete example, let's suppose that this is our matrix. So then, if I use this entry as the shift, and I go ahead and take QR factorization of a shifted matrix, then multiply the factors in reverse order, then shift back, then here's the subdiagonal entry at first, 0.0975. Now, first it gets a little bigger. That's not what we want. Then it starts to get a bit smaller, so 0.0038. And then I keep going, and we get something in the order 10 to the minus 5. So the number of 0 decimal places has doubled. And then 10 to the minus 10. So this is illustrative of quadratic convergence. That we take this number and square it, and we get something that's on the order of magnitude of this. So that's going to 0 extremely rapidly. So I'm actually going to do a quick Matlab demonstration of this. Okay, so I need to unshare and reshare. Where's my Matlab window? Okay. All right, so here's my matrix, A0. So it's a Hasselberg, a randomly generated Hasselberg matrix, and fortunately, it happens to have real eigenvalues. So that's helpful for this demonstration. Okay, so all right, so set A equal to this matrix A0, and so what my shift, I will select the n entry, so a 5, 5 entry. And And then, actually, first I want to create an identity matrix, just for convenience. Okay, so now I will select the 5 entries, my shift, and then I'll compute the QR factorization. Sorry. I keep forgetting to do a diary of this. All right. All right, so there's my 5x5 identity. So now I set my shift, do the QR factorization of a shifted matrix, and then multiply the factors in reverse order and shift back. So let's see what happens to this last subdiagonal entry as I proceed. All right, so first, nothing really happening yet, because we're not necessarily close to an eigenvalue. But then I keep going. All right, so in the order of 10 to the minus 3. And then again, see, it's gotten a lot smaller still. So now it's in the order of 10 to the minus 7. And then one more time. And look how tiny it's gotten. So this also is illustrative of quadratic convergence. So this is why, because quadratically convergent methods, you only need to carry out a few iterations and you're done. You're getting all the precision that you can reasonably expect to get. So now we have some theory to back up that we only need to do a few of these iterations per eigenvalue, that the problem decouples and then we work with a smaller matrix. So that will certainly help to make the algorithm a lot faster than it was. All right. Are there any questions up to this point? Okay, I need to go back to the notes. All right, so I'll include that diary with the other stuff. Okay. Now, before continuing, or talk about drawbacks of this approach, one thing I want to explain is to why Singleshot strategy helps with convergence. So if these are the QR factors that I get during the iteration, and I multiply them all together to give me QK hat and RK hat, then it turns out that we have this, that QK hat, RK hat comes from this product of the original Hasselberg matrix, H1, minus each shift. In fact, proving this by induction is one of the homework problems from this section. So have fun with that. Okay. All right, need to fix my equation reference here. So this would be equation 2. Okay. So another way of putting it is if I take the transpose of both sides of this and then multiply by QK hat to rearrange the equation, then this is what I get. Now, what's interesting about this is what this equation is saying is that the columns of QK hat come from applying what's called inverse iteration to H1 transpose with these shifts. Now, what is inverse iteration? I've not talked about that before. Inverse iteration is a power method, but applied to this matrix, A minus mu I inverse, for whatever general matrix A. So a power method, you keep multiplying by A, and that gives you the largest eigenvalue. Inverse iteration, instead of multiplying by A, you're multiplying by A minus mu I inverse. So you're solving a system of equations, an AX equals B problem in every iteration. And then that means you're finding a largest eigenvalue of this matrix. But the eigenvalues of this matrix are 1 over the eigenvalues of A minus mu I. So inverse iteration finds the eigenvalue, instead of the largest of A, it's finding the eigenvalue of A that is closest to mu, whatever shift you're using. So it's a way of finding eigenvectors corresponding to any eigenvalue, not just the largest. There's also a way to like target it, to find a eigenvectors associated with specific eigenvalues. Because if you get the Schur decomposition of an unsymmetric matrix A, you have the eigenvalues, but you don't have the eigenvectors. You have these Schur vectors, which are not all related. But what you could do, if you only want selected eigenvalues, you could just use inverse iteration on the known eigenvalues that you have. And maybe you'll perform just one iteration. And then you get a highly accurate eigenvector. So what this is saying is each QR iteration with these shifts is also, you could think of it as an iteration of a power method applied to this matrix where the shift is changing every time. So that would have the effect of finding eigenvalues that are close to your shifts. Now, when your shift is an approximate eigenvalue, inverse iteration converges very rapidly. And these shifts are already known to be approaching some eigenvalue of a matrix quadratically. So in fact, what this is effectively doing is performing inverse iteration. It means that now, I want to point out here that if I look at this matrix, this is what you get after carrying out all those QR iterations. And then by multiplying by En transpose on the left and En on the right, I'm taking the NN element. And so that's going to be HK plus 1. So this is the last diagonal entry of a matrix that results from all these QR iterations. But that is a Rayleigh quotient. And recall that if you have an eigenvector, the Rayleigh quotient gives you the eigenvalues. So the Rayleigh quotient of H1 in the last column of QK hat is the shift for the next iteration. And because we're applying inverse iteration to the transpose, then it turns out that the last column of QK hat, so what this equation is saying is this last column of QK hat is converging to a left eigenvector corresponding to the eigenvalue that you're converging to. I missed. Yeah. Okay. So this gives some insight into the behavior of basically giving an idea as to why this repeated shifting QR factorizing actually works. Because it can be seen to literally be an instance of applying a iteration that is known to rapidly converge to an eigenvalue eigenvector pair. Okay. So this is good progress, that we can get the eigenvalues much faster than before, but we're not done yet because this approach doesn't always work well. Because, hold on. What if your Hasselberg matrix has complex eigenvalues? Then if you're choosing the nn element, which is real, to be a shift, it's not going to be close to one of these complex eigenvalues. You won't get that kind of convergence. So what can you do instead? You can use what's called a double shift strategy. So if you look at, instead of the last element of H, if you look at the lower right 2x2 block, you can check if its eigenvalues are complex. And if they are, then you can use those as shifts. So you can carry out 2 iterations, one with each eigenvalue in its complex conjugate pair. So here's what you do. You just carry out 2 iterations like before. You shift and QR factorize, multiply in reverse order, and shift back. That part is no different. It's just that you use mu1 and then its complex conjugate mu2. So that's one thing you certainly could do, but the problem is that this brings in complex arithmetic, and we really want to avoid performing complex arithmetic because each individual operation, distance, subtraction, multiplication, division, significantly more expensive when it's complex. So what can we do about that? We use what's called the double implicit shift strategy. So what does that mean? So if these are our 2 shifts, our 2 complex shifts, then their sum and product are real. So if I take these 2 matrices involving these shifts and FOIL it out, then what we find is even though these shifts are complex, this matrix is real. Now, how does that help us? I need to check my equation references here. Something looks odd here. Need to check something in the book. Okay. I hope I don't have a flawed equation reference. Oh, okay. No, I don't. Oh, dang it. I hate when this happens, how the text gets smaller. Okay. Now it's too big. Sorry, just bear with me a second. Okay. So this should say equation 2 from before. That M can be expressed as the product of the Q's from these 2 iterations times the product of the R's from those 2 iterations. Now, why this matters is since M is real, Q1 and Q2 are orthogonal. They come from a QR factorization. Therefore, their product is orthogonal. R1 and R2 are upper triangular. Therefore, their product is upper, so this is orthogonal and this is upper triangular. This is a QR factorization of a real matrix. Now, the QR factorization is unique. So it doesn't matter how we arrive at it. That so what we could do is we could form M and then take the QR factorization, and then we'd have at least we wouldn't have Q1 and Q2 or R1 and R2 individually, but we would have their products. Now, why that is helpful is the following. If I look at the final result of these two steps, because if we look back, we start with H, we perform a QR step, we get H1. We perform another QR step with a conjugate shift, and H2 comes out. H2 is what we want. If we take a closer look at H2 and how it was obtained, but then through all these manipulations involving QR factorizations involved, what we get is H2 is obtained from the original matrix H by this similar transformation involving Q1, Q2. We don't need to know Q1 and Q2 individually to get from H to H2. Knowing their product is enough. And we know how to get the product by QR factorizing M. Okay. So now we have a way to avoid complex arithmetic. What we can do is go ahead and form M, knowing that that's a real matrix. Then we compute its QR factorization, which call ZR, where Z is Q1, Q2, because the QR factorization is unique. And then we go ahead and compute this, which this would be Z transpose HZ. And then we have H2. So M is real, therefore the QR factors are real. Everything involved here is real. So we've managed to avoid complex arithmetic by taking advantage of the fact that the QR factorization is unique. But there's one huge drawback to this. It's actually a deal breaker. Look at how we compute M. Up here, we're taking a second-degree polynomial of a Hasselberg matrix H. We are squaring H. That's an order n cubed operation. Now, we'd already gotten to the point where each QR iteration requires only order n squared operations. To QR factorize a Hasselberg matrix and multiply the factors in reverse order is also order n squared. So now we've it's basically taking a step forward and two steps back. Now our iterations are made too expensive again. So it defeats the purpose of going to Hasselberg form in the first place. So we can't do that. But can we still use this idea to arrive at something that is practical? And now we're getting to the main achievement of the two individuals who invented this QR algorithm independently of one another, using the theorem I mentioned last time, the Implicit Q Theorem. So what we do is we don't form M completely. We only form a first column. Now, that's not a problem. A Hasselberg matrix has only 2 non-zero entries in its first column. If you square it, it's only going to have 3 non-zero entries. So that's a piece of cake to go ahead and compute those. And then we found a household reflection that zeroes out the last 2 non-zero entries of this first column. So in other words, we're zeroing out everything except the first entry. Now, why is this important? Because this process that we wanted to do, but it's too expensive, what does it involve? We form M and then we take a QR factorization of M. If we did have M, what would the first first step in computing is QR factorization B. We make a householder reflection that zeroes out the subdiagonal entries of a first column of M. Remember, this householder QR factorization works from left to right, first column, second column, and so on. So this is a householder reflection that starts that process. Okay. Then what? We actually apply this householder reflection not to any part of M, but to H. Because H is a matrix we're trying to transform in the first place. So we apply it to H. Now that wrecks the Hasselberg structure, but that's okay. Because what we do now is now we apply more householder reflections for each column, starting from first column, second column, and so on, that will restore Hasselberg form. So we make it un-Hasselberg a little bit, and then we re-Hasselberg it. Yes, I just made Hasselberg into a verb. Now, here's the key idea here as to why this works. Now, we're only trying to use these householders are only meant to make the matrix Hasselberg, this matrix. Now, for an example, in the first column, we want to keep the first two non-zero entries. We want to wipe out anything below that. So that's going to affect rows starting from row 2 on down. They don't touch the first row when you multiply on the left. They don't affect the first column when they're applied on the right. So now, if I define Z tilde to be the product of all of the householder reflections, this one as well as these, then it turns out that because these do not affect the first column of P naught, it turns out that Z tilde has the same first column as Z, the matrix that is used to reduce M to upper triangular form. In other words, so at least if you're looking at the matrix that upper triangularizes M, Z and Z tilde have the same first column. And why that is essential is the following. Z from before, when applied to H, keeps it Hasselberg, because H2 is also Hasselberg. And because Z and Z tilde have the same first column, and Z tilde also makes H Hasselberg, that means they're essentially equal. So, so the matrix that they produce is the same. They're not exactly equal, but the subdiagonal entries in particular, they would have the same absolute value. And that's very important because we're looking for those entries to become 0 so we can spot decoupling. So really, you think of this as instead of saying fake it till you make it, we make it by faking it. We pretend that we're going to start QR factorizing M without forming the whole thing. And then we make sure that when we apply this transformation that we keep the matrix Hasselberg. And because of the implicit Q theorem, that turns out to exactly simulate what we would wanted to do earlier, but turned out to be too expensive. So this is still being done, but by a different route and taking advantage of the implicit Q theorem that gives us enough information to figure out how to end up triggering the same transformation, but without forming all of M. Only forming a first column is enough. That's the trick. That's the stroke of genius that makes this algorithm practical. So this is called a Francis QR step that actually gives us the first practical algorithm for computing all the eigenvalues of a general square matrix, whether they be real or complex. Um, so we had a good shifting strategy, the Singleshot strategy, which is great for real eigenvalues, but it didn't help for complex. We could use complex shifts, but we didn't want to do complex arithmetic. Um, we saw how to avoid complex arithmetic, but that was too expensive. But by using the implicit Q theorem, we found another way to carry out the same thing. Okay, so each QR step requires this many operations, order n squared. If you're trying to accumulate transformations, oh wow, it's looking terrible out there. Um, do I have an umbrella? Oh, yeah, I do. Okay. If you're trying to accumulate the orthogonal transformations to get the whole real sure decomposition, then there's extra expense in doing that. You would not do this if you only wanted the eigenvalues, then it just costs this much. Putting everything together, including the Hasselberg reduction, the entire QR algorithm takes order n cubed operation, so 10n cubed. So it's significantly more expensive than like Gaussian elimination. Gaussian elimination takes 2/3 n cubed operations, but the constant in front of the n cubed is larger in this case. If you want the Q from a real sure decomposition, it takes a whole lot more. And this could be used to eventually get to the eigenvectors, which I won't get into here. There's some implementation details. Every time you carry out a QR iteration, you want to look at your subdiagonal of H. If an entry has become 0, you want to decouple, and then continue your work on a smaller matrix to find the remaining eigenvalues. Because if this is still pretty expensive, order p squared for p by p matrix. But if you could make p smaller, then that definitely speed things up. And generally, you're able to decouple after performing just a few QR steps. So it gives you an idea as to the overall operation count. Okay. And I've actually come to the end. So I will admit that when I remember studying all this back when I was a student, it definitely took some work to wrap my head around like why this all actually works. And I found myself doing a lot of diagrams of matrices and seeing what these transformations do and so forth to convince myself of various things that I've laid out here to see like, oh wow, yeah, this really works. That if it's use of the implicit Q theorem. And it just goes to show why it's so important to understand how all the different operations we perform, like given rotations, household reflections, etc., affect the structure of a matrix in terms of what's zero or non-zero. What are certain columns or rows of matrices you're working with? That understanding all of these things is what leads to algorithm improvement. And we still have some material to cover with eigenvalues because next week I will talk about the symmetric eigenvalue problem. So when the matrix A is symmetric, a number of simplifications can happen that we'd like to take advantage of to make the algorithm a whole lot faster. Um, and also the algorithm for the SVD, the singular value decomposition, that was my advisor's crowning achievement of his career. Where ideas from the symmetric eigenvalue problem are adapted to compute the SVD, because we've dealt with the SVD, but I never explained how it was obtained. So now that I've covered all this, I'll be able to explain that to you too. Okay, so questions about anything, including any homework problems? Walker, I'm glad you were able to make it.
I'm at T-Bone's outside at the patio, and it's so loud with the rain, but I got my headphones.
You're outside right now?
Yeah, but in the patio, but it's kind of cool watching the rain with class at the same time.
Okay, well, as long as you're adequately sheltered.
Yeah.
Thanks. Okay, so any questions from anybody? I'm glad that class was a little short. Those of you who are about to join PDEs, I have a feeling that will be short too. um, I wonder if you want to check on the assignments page of a site. Okay. I haven't posted it on the course website or in Canvas, but I do want to mention this. Um, what I've historically done in this class is when we get to the fourth homework that's on the eigenvalue chapter, that I give a choice. You can either go ahead and do that assignment, or there's an alternative that is a coding project that involves implementing the algorithm for a symmetric eigenvalue problem. So it's laid out like, okay, here are functions you need. Here's the bits and pieces from a course material that you would use. And doing things like givens QR factorization and things like that. Generally, not many students have chosen that option, although some have. And um, so if you'd like to do that instead of a fourth homework, let me know. And if there's some interest, then I will post that. So I know some of you are like, when it comes to MATLAB, um, which can be unfortunate in a class like this one, but at the same time, in the regular assignment, you're proving stuff, and that could be unappetizing too. Um, so up to you. Actually, I'll probably end up posting it anyway. But if you want to try that instead, just let me know. Okay, so since you're really usual, quiet bunch as usual, I'll stop recording here, and then I will, as usual, see some of you in PDEs in about half an hour.